Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments, and we're doing a little mini series on split plot design. This is part 8 of 10, and we're going to look at the distribution of the sums of squares. In the previous two videos in this mini series, we partitioned the total sums of squares, and then we derived the expected values of the sums of squares. And now we're going to derive the distribution of each of these sums of squares. And we're going to do it for the split plot RCB. Now this is my notation. I would encourage you to watch part 1. But it essentially means that the first factor, what we use to randomize complete block design to randomize it. And then the second factor, of course, is always done the same way. So here's the model: y equals ijk, yijk equals mu plus epsilon I plus beta j plus this whole plot error term, gamma k, the interaction, the split plot error terms. They're both normally distributed, they're independent. Now, the distribution of the y vector is multivariate normal, has a mean x beta star, and it has this covariance matrix, and we derived it in part 1, and we've also derived it in other videos in this mini series. Now we're going to look at the distribution of the sums of squares for alpha divided by this constant, which is part of this. Sums of squares for alpha is this part, y transpose m alpha minus j y. And these are perpendicular projection matrices onto certain column spaces of the design matrix. And I encourage you to watch parts 3 and 4 in more detail for that. But if we just generically call this middle part here A, then this is a quadratic expression. And I have a playlist for quadratic forms, and in there I have, I think it's 3 or 4 parts on the distribution of the quadratic form. And I encourage you to look at that if you need more information there. But essentially, we need A times the variance of y. It must be idempotent for this theory to work. And in part 7, we showed that it equals this perpendicular projection matrix, which is idempotent. And we've also shown that the rank of A times the variance of y, which is the rank of this, and so it's going to be t minus 1. So that says that the distribution of y transpose A, where A is this piece here, it's a non-central chi-square distribution with t minus 1 degrees of freedom, and it has a non-centrality parameter of the mean of y transpose times A times the mean of y. And now this piece here we examined in the previous video, and it has this scalar form. And that's it. So this is distributed with the chi-squared. Now, if we look at the sums of squares for whole plot divided by this constant here, which then the sums of squares error for whole plot is this. And so if we just generically call this middle part B, then this is a quadratic form. And then we have to show that B times the variance of y is idempotent, which we did in part 4. And the rank of it ends up being the rank of this perpendicular projection matrix, which is TR minus TR plus 1. And it can be factored into this. So the sum of squares error for the whole plot is a non-central chi-squared, with this degrees of freedom and this non-centrality parameter. But in part 7, we showed that this was 0, so it ends up being a central chi-square distribution with this degrees of freedom. Now, this distribution here, when we're looking at the sums of squares for the block, we're often not interested in testing the block effect. But if you are, then it can easily be shown that this is a non-central chi-square distribution with r minus 1 degrees of freedom. and this non-centrality parameter. And we also derived this in the previous video. So here the sum of squares error for the split plot is divided by this constant is this. So this first part is the sums of squares error for the split plot, and then of course the constant. We can just generically call that C, and we have to show that C times the variance of y is idempotent, and this ends up being this matrix, which is, you can see part 7, but this is a perpendicular projection matrix, and so it's idempotent. And the rank of A times the variance of y ends up being the rank of this matrix, so that's N minus TR minus TM minus T. Now N is of course the number of observations, T is the number of treatments, R is the number of blocks, or the number of reps if we use the CRD design. M is the number of treatments for the second factor. T is the number of treatments for the first factor. Then, since these two properties hold, and y is multivariate normal, then y transpose C is a non-central chi-square distribution with this degrees of freedom and this non-centrality parameter. But in part 7, we showed that this was 0, so it ends up being a central chi-square distribution. The sums of squares for gamma divided by this constant is this in quadratic form. If we call this middle part D, then in part 7 we showed that D times the variance of y is just this matrix, which is a perpendicular projection matrix, so it's idempotent. The rank of it is m minus 1, so it's a non-central chi-square distribution with degrees of freedom m minus 1 and this non-centrality parameter. And in part 7 we showed that was this in scalar form. Then the sums of squares for alpha, or the interaction space between alpha and gamma, divided by this constant, it's this quadratic form. And if we call this E, then we can show that E times the variance of y is this perpendicular projection matrix, which is idempotent, has a rank of T minus 1 times m minus 1. So it is a chi-square distribution, non-central chi-square distribution with this degrees of freedom, and it has this non-centrality parameter. And then in part 7 we showed that in scalar form it is this. Now this becomes important. Next video we're going to look at the F tests associated with the different sums of squares, and it makes a difference. Notice that in some of these we only divide by sigma s squared, or the variance associated with the split plot randomization, right? And then others we had to divide by this constant, right? So the F tests become important, which error term we have to use when we're doing which test. And then we'll highlight that in the next video. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.